All right, so we're going to talk a little bit about use substitution. Hopefully those problems went okay in groups. So use substitution is basically a way to work backwards from the chain rule. It's going to turn out that antiderivatives tend to be much more difficult than derivatives. And so at this point, basically any function I give you, you can take the derivative of it. It might be a little messy, it might require multiple formulas, but you can find the derivative of it. In general, if I give you a random function that's sort of messy, you will not be able to find the antiderivative of it. Sometimes there isn't even an antiderivative at all, which is sort of weird. So in general, in this class, when you come across something that you're supposed to find the antiderivative of course you will be able to find it, and oftentimes guessing and checking is perfectly acceptable. Try something, see if it works. If it doesn't, oftentimes right as you're checking it, you'll sort of see how to adjust your answer. Sometimes though, use substitution is nice to work with, and it's when you're working with the chain rule. And so the big idea is when I look here, I see a product, right? And so I see this sort of more complicated thing, and I see the x squared is the more complicated thing. And so what I would usually do then is I'm just going to rename the inside thing u, right? Hence the name use substitution. So I'm just going to give a new name to x squared, and I'm going to call it u. Then I'm going to take the derivative, and so I'm going to write that as du, and I'm going to write 2x dx. And this is just sort of a bookkeeping thing. Instead of writing du dx, I moved the dx over here so that all the x's are together and the u's are together on the left. And so now I'm going to try and rewrite this integral in a little bit cleaner way without the x's. I'm going to use u's. And so when I rewrite it, well, this is easy. This is just e to the u. And so that's going to be nice and simple, which is good. But I have to account for this x and this dx. Oh, well, this is good. I've got an x and a dx here. The only problem is this 2, right? There's no 2 out here in the original problem. And so I need to get rid of the 2. And to do that, I just move it over here, and I see that, oh, now when I get rid of it, x dx is 1/2 du. So when I go up here, my new integral is e to the u 1/2 du. And so I just have to make sure I accounted for everything, right? This is covered in the e to the u. These two things are covered in the 1/2 du. I don't have anything extra, so I'm good to go. The nice thing is this integral is much easier. The 1/2 is just a constant multiple, so that just sits there. What has a derivative of e to the u? Well, that's e to the u. And so I'm basically done, right? The only catch is, of course, I started with x's, so I have to end with x's, and so I'm just going to substitute back in and say, oh, u was x squared, right? And then I won't forget my plus c. Again, take the derivative of this. How are you going to take the derivative of this to check? The 1/2 sits there. E to a power is its own derivative. Multiply by the derivative of the inside, 2x. Sure enough, the x's or the 2's cancel, and I'm right back where I want it to be. So I know I'm right. Right? Notice how fragile this is, right? This had to work out perfectly with the chain rule. If this x had been an x squared, it wouldn't have worked. If this x hadn't been here, it wouldn't have worked, right? Before winter break, we will learn a couple other techniques, like if I change this to an x squared, no one might know how to do that yet, but we will learn a technique for that before winter break. So that's sort of example one. Why don't you pause it for just a second, talk to your neighbor, clear up any questions before you go on to the second example. Okay, welcome back. So here's another one, sort of similar to some of the ones you did on the worksheet. So I'm going to look at this. I'm going to look at the more complicated thing. This is the 4 makes it more complicated. And I'm going to let u be the inside of the more complicated thing, right? Not the very inside, but just sort of the next level down. So u is cosine of 3x. So du will be negative sine of 3x. I'm taking the derivative, and the chain rule kicks out that 3, and then dx. And so now when I go to rewrite this, right, what am I going to have? Well, I have cosine of 3x to the 4th, and so that's u to the 4th, right? So that takes care of that whole mess, obviously much simpler. And then I need a sine 3x dx. And so I see a sine 3x dx there. And of course, the only things that's messing me up is the negative 3. So I'm going to move the negative 3 over here. And so now I know what sine 3x dx equals. It equals negative 1/3 du. So now this is a much easier antiderivative. That negative 1/3 is the constant multiple. It just sits there. What's the antiderivative of u to the 4th? I add 1, and then I divide by the new power, right? And so I divide by that 5. And so my new antiderivative is negative 1/15. What's u? U is cosine. And so I could just write that like this. And then I put my plus c on the end. I'll leave it for you to check this with the chain rule. If you check this with the chain rule and go through the couple steps, you should end up with exactly what we had started with. And so this is the general antiderivative. All antiderivatives of this original function would have to look like that, where c is just some real number. This is always a little weird when you first start doing it. So once again, I'm relying on the people who had calculus last year, sort of adopt a person or two who hasn't done this. As you're working on the worksheet with tons of practice problems, help them out, answer questions, and have a good productive day. And we'll obviously talk more about it tomorrow.